Of last Wednesday was s orbitals overlapping. We could also do this with p orbitals. P orbitals become a little bit more complex because we have two lobes. So oftentimes you'll see them colored differently because they stand out a little bit different. If you're in a textbook, you'll usually see them literally different colors. If you're seeing them for whatever I produce it with the thought of printing it, and because I'm cheap, I don't want to print color. So they're always kind of grayscale, so black and white, kind of a deal. Okay, but what those are supposed to represent are the two phases of our orbitals. So we can get positive and minus. Remember, because we're looking at electrons and they move in waves, we get a positive phase and a negative phase, all right, with that wave action. If we go through and look at our p orbitals, okay, and we bring them together along the x-axis. So we're taking 3 p orbitals from one atom, 3 p orbitals from the other, and we just bring them near each other along the x-axis. What's the very first thing that's going to happen? Which orbitals are going to be most likely to interact between those two sets? So we're saying we're going on the x-axis. There's our x-axis. This is the z-axis coming out at us. Here's the y-axis. If I bring an atom, which of those orbitals, I know those look awful. Try and color it. There's our z. There's our y. And here's our x. Which are the most likely to interact with the next atom over? Looking exactly similar to this. So we copy and paste and start drawing them closer to each other. Which orbitals are likely to interact first? The green one, the one on the x-axis. Okay? The reds and the blues aren't on that axis. They might overlap parallel, okay, but they aren't going to directly overlap. So if we were to look at this system, really what we're saying is we are overlapping, assuming I labeled these right. Well, it looks weird, whatever. We would overlap 2px, assuming we're on that x-axis. Okay? In the case where they were all in phase, let's try and make everybody a little bit happier today and say it's the optimists. Okay? Those positives now interact with each other, which means we increase the probability of finding electrons there. If we use black dots as our nuclei, black dot, our hybrid of these now, we're increasing the electron density in between, we're decreasing it on the outside, and we get a little candy wrapper. Okay? What happens if they did not come into alignment? Okay, what if it was positive and negative? Well, now we decrease the probability of finding the electrons in that space. And we get something along those lines. Okay? Notice directly in between, again, we get a space of 0 electron density. There's a node. Okay? We move up in energy, we get a node. Right? I brought 2 atomic orbitals together. How many molecular orbitals did I make? 2. Okay? The very first one in purple and the top one in red. Those are 2 molecular orbitals. Okay? They describe the bonding of the molecule. Okay? If I want to be able to distinguish those molecular orbitals, I could come up with names for them. Okay? In this case, we're looking at a direct overlap of orbitals. So we might reference this type of bonding as sigma. The bottom one would be a sigma bonding because we have a favorable interaction of those orbitals. We've increased the electron density between the atoms. The top one is still a direct overlap, but those overlaps canceled out. So while this is still a sigma-type interaction, we're not forming a bond. But this is not a bond. This is actively not a bond. which means we can't just call it not a bond. We invent a new term, our antibond. And we can drop in the star on our representation. Right? So we get a sigma bond and a sigma star or a sigma antibond. Okay? Kind of, sort of? Okay? What about the py and the pz? Right? Because the y is easy to draw. Would we get a direct overlap? No. The px prevent the direct overlap because they've formed that connection. It can't get any tighter because then we start getting nuclear repulsions. Okay? So we just get a distance where those py's are now kind of in the same plane, but not directly overlapping. That distance happens to be close enough that we get electron tunneling, and our electron can jump without ever occupying that space to the other position. Okay? Because the electron has that ability to jump kind of in phase, we could now look at that positive-positive relationship. And yes, this is going to get really crammed, so let's kind of shrink that a little bit. Where the electrons now move back and forth. So we could shade the top lobe. I did a horrible job doing that. Let's try that again. And we would get something looking like this. Okay? Where the electron is able to jump across that larger distance. Notice, what do we still have running through the middle? A node. We still have the p orbital node. What would happen in the positive to negative case? Well, now they don't overlap. So what happens? We'll get the electron clouds pushing away from each other. Okay. We still get the node running through the middle, and we also get a vertical node. Okay. What we're representing is the different layers of bonding all the way through this. This is now a new interaction. White was the wrong choice, whatever. That new interaction down here is now not a sigma bond. Okay, it's also not a sigma antibond because we actually have electrons existing between the nuclei. What kind of overlap is this? It is a pi type overlap where we have an indirect overlap of the orbitals. Right? So this will get referenced as a pi bond. Right? The one up above gets referenced as a pi antibond or a pi star because the electrons are actively avoiding the space in between the nuclei. Okay? And we now end up with some more molecular orbitals if this was the type system that we were looking at. We could also do it with the PZ, the ones coming in and out of the plane at us, but those are going to be really confusing to see. Right? Ultimately, are those any different than the PY? Do they still involve p orbitals? Yeah, so they're identical, which means when we look at the pi bonding and the pi antibonding, we will get two sets. Okay? And by set, we're referencing both the pi and the pi star. Okay? So if we clean it up and get rid of all those pictures, can I get rid of all the pictures?
Yes.
We form a sigma bond. We formed a pi on the y-axis. We also formed a pi on the z-axis. Okay. We also have a pi star on the y-axis and a pi star on the z-axis. And then we have a sigma star. Okay. And we now have our molecular picture for these two atomic systems. Where we were referencing the direct overlap of our p orbitals. Okay. How many molecular orbitals do we have? There are literally 6 lines, there are 6 orbitals. I don't care that those are anti-bonding. Those are still molecular orbitals. Okay? Don't use the term anti-bonding to mean there's not an orbital. There's absolutely an orbital there. It can absolutely hold electrons. Okay? How many atomic orbitals did I start with?
6.
Okay, we had 3 atomic from one atom, and we had 3 atomic from the other. Note, when I add all the atomic orbitals up, what do I end up with? 6. The molecular orbitals match out. Orbitals are just like matter. We can't create or destroy them. So I can look at my atomic picture, say I've got 12 orbitals, 12 atomic orbitals. Well, how many molecular orbitals would I expect? 12. Right? When we go through and look at our molecular orbitals, are they all the same? Is this sigma down here the same as this sigma star up there? Is a sigma the same as a sigma star? No, and we know that because I said star. This line is down here. This line is up there. Are they the same? No. Okay? Keep it simple. What kind of pattern do you see with those 6? How do they split? Stars are on top. How many stars on top? How many stars on the bottom? How many did we start with? 6. What if I started with 12? 6 antibond, 6 bonding. It's always going to pattern out like that. Okay? With one pseudo exception, that pseudo exception being this is all talking about bonding, right? Is there a type of electrons that aren't involved in bonds? Yes. That we might call
Lone pairs.
Lone pairs, or literally non-bonding electrons. Where would the non-bonding electrons fall in our diagram?
Probably in the middle.
Right through the middle. They're not contributing to the molecule. They're non-bonding. That's why they exist right in the middle. Okay, so you could see weird splits like that with those. Kind of makes sense? Okay. When we look at our atomic models, we looked at the pure S and the pure P. Realize that that model, while fantastic, really requires a computer program to go through and calculate the details of all those orbitals, okay, to get the exact energies and all that fun stuff. So we don't really use the full linear combination of atomic orbitals. Instead, what we use is a hybrid version of it. What do we hybridize it with? What might we hybridize it with?
Hybrid orbital.
Hybridization theory. Okay, so when we go through to look at our sigma bonds, what we're referencing is S-type orbitals, the sp hybrid orbitals. When we talk about our pi bonds, we're talking about leftover p orbitals hybridizing. So when we look at our pictures or try to scale things out, that's what we end up tweaking it to. So if we look at something like this, which may be kind of difficult to process, but the formula is given there. Carbons, I can go through and draw those instead of pointing. Maybe, come on. We've got our carbons in the middle, and then we have our hydrogens out on the outside. So if we were to go through and look at this structure, here's our Lewis structure. How many sigma bonds do you see?
5.
Whoops. Here's one sigma bond. Here's a second, third, fourth, fifth. There is no more double bonds or single bonds. They don't exist. They're either sigma or pi. Okay? That first interconnection, the first bonding orbital or the first bonding interaction between any two atoms will be a sigma. After that, if I want more bonds, I have to layer in a different type of bond. That's where I get the pi. So if we go through and look at this, we've got 1, 2, 3, 4, 5, I lost track of counting, 6 different bonds. which means I'm going to have 6 bonding, 6 anti-bonding, which would mean I would need 12 atomic orbitals to account for that. Yes, this is kind of cheating and saying they're all there, but what are those 12? What is the atomic orbital being contributed by hydrogen?
S.
I kind of accept S. We can do better. We can do better. S1 is now telling me how many electrons are there.
1S1.
1 S1, how many of them are there? There's 4 because there's 4 hydrogens. So there's our 4. What is our carbon contributing? Okay, I will accept a P, and sort of, I won't accept a P. I will accept a 2P. There's 2 of them there, which would get us 2 to our list. What else does carbon have?
2S.
No, our 2s would work great for the linear combination of atomic orbitals, considering that only 4 people have computers out, and those computers do not have enough brain power to process that. We don't want to use 2s orbitals. We want to use the sp2. Where are the sp2 coming from? Take a look at your carbon. How many groups of electrons around that carbon? 3 groups of electrons. 3 groups of electrons equals sp2. Use your superscripts. 1 plus 2 equals, that says 1 plus 3, referencing our 3 groups of electrons. The pi bond is not an extra group. It's the exact same face. So it does not count as a distinct group. It's wrapped into the same thing there. I don't care how many electrons are on a face of that. If there's electrons there, that is one group. I could have 50 billion electrons. I can't, but let's just say I did. That's one group. Okay? 3 groups of electrons means sp2, which means carbon is also going to be contributing sp2 hybrid orbitals into this. How many sp2 hybrid orbitals is carbon going to contribute?
3.
Remember, there's 3 groups of electrons. So we picked sp2 so that I could get 3 interactions, 3 equal groups going in. So my carbons are going to generate 3 sp2 hybrids. But how many carbons are there? Which means I get a whopping total of 6. Which brings this all together to a total of 12. There's our 12 atomic orbitals. Okay? How would I expect those to split out in the molecular orbital diagram? Right? Remember how we drew all those overlapping? You're like, how are we going to do that with something this complex? We won't. We'll cheat. How many of those bonds are sigma bonds? 5. Which means if I'm going to look at my diagram, I'm going to have sigma bonds down here. How many sigma bonds am I going to have? 5 sigma bonds. But if I have sigma bonding orbitals, what am I also going to generate? Sigma antibond. How many of those am I going to generate? 5. What would be left over? Because that looks like 10, right? 5 antibond, 5 bonding. I need 12 atomic orbitals, which means I have 1 pi bond left over with 1 pi antibond. If we go back and look at our diagram, how many pi bonds did we make? 1. Okay, 1 pi bond. If we were to now drop electrons into this diagram, because at this stage all we've done is said there are orbitals, but we haven't said how many electrons are there. For instance, if I look at hydrogen, where's its electron? A 1s orbital. How many electrons do you place in the 7s? None. Why not?
Hydrogen doesn't have that many.
Hydrogen absolutely has a 7s orbital.
No, hydrogen doesn't have that many electrons.
Okay. The orbitals exist. That does not mean electrons populate said orbitals. Okay? These are now all of our orbitals for this molecule. Okay? If we look at hydrogen, it has a 7s. If we look at ethylene, we have sigma star. Which of those orbitals have electrons in them? Well, with hydrogen, you knew how many electrons belonged to hydrogen. How many was it? 1. So you place that 1 electron in the lowest energy orbital, 1s1. Cool. How many electrons belong in this molecular orbital diagram? Well, you told me you knew how many electrons hydrogen had, right? That is 1, right? How many of them are there?
4.
Do you know how many electrons carbon brings in?
4.
How many carbons are there?
2.
12. If we were to go through and start populating our orbitals, where are we going to place electrons?
Lowest energy.
Lowest energy first. How many orbitals do I have for my sigma bonding? 5. How many electrons go in? 10 electrons. Is that all my electrons?
No.
No. Where's the next set of electrons go?
Next lowest.
The next lowest, which happens to be the pi bonding, and we get our 2 electrons there. How many electrons are in the anti-bonding?
0.
None. Okay. So if we look at our molecular orbital diagram, we've placed all of our electrons in bonding type orbitals. What would that suggest about the validity of this structure?
That it is valid.
That it is valid, that we would expect all of those bonds. What if we'd populated more electrons into this? If we put more electrons in, we start to destabilize the molecular orbitals. And what happens? It falls apart. The molecule starts to react. So when we're looking at how we can potentially cause reactions to occur, it's a lot about electron donation or electron accepting. Right? Which electrons for this molecular orbital would you expect to be donatable? Why the pi ones?
Because that's the outermost and you can't.
Good choice with outermost. I don't like your outermost word choice. We'll come back to it in a second. What do you got?
They're accessible and they're highest energy.
These are our highest energy electrons. They're highest energy because they're outermost. Right? So we could call these energy molecular orbitals, right? Okay. If this molecule was to accept electrons, where would it accept electrons?
The lowest unoccupied molecular.
I would probably go in the antibond. Which of my antibonds should I put electrons into? Pi star or sigma star?
Pi star.
Why pi star? It's the lowest energy molecular orbital. Okay, and we're going to challenge that in just a second here, but I got to write all those stupid letters and words down. Lowest energy molecular orbital. And as you might guess, writing all those things out is tedious. For those of you that are actually writing it out, you might want to stop writing that down. You're really telling me that the pi star is the lowest energy molecular orbital. The pi isn't lower in energy? Isn't the pi lower in energy than the pi star?
But it's occupied.
So is low energy and high energy the best reference?
No.
No. What are we indeed referencing in this case?
Occupation.
The occupation of electrons. Okay, so we aren't really saying low and high energy. We picked the high one because those were the highest energy electrons, okay, that occupied that orbital. So this is the highest occupied molecular orbital. And our pi star is the unoccupied, which is why we reference the pi star in this case as the LUMO, lowest unoccupied molecular orbital. So for those of you breaking your wrist writing that all out, that's why we write LUMO. The bottom one for our pi is our highest occupied molecular orbital, and we get our HOMO. Virtually all chemistry is, virtually is kind of the improper term, because all chemistry sits in dealing with looking at how the HOMO and LUMO of individual species align energetically. But that would mean we'd have to quantify each of those energies. Okay? And while some of you may be excited about quantifying those energies, I am not. And all we're going to do is reference that we have these HOMOs and LUMOs, and that if a reaction occurs, we have the proper alignment. What do I mean by the proper alignment? If I want these pi electrons to react with something, where would they need to go? They would need to go into
Similar energy level bonds.
Okay, so now we got to bust out the eraser. So I like some of what was suggested there. They need to go into something else. Okay, so we would need another system next door. Okay, so here's our reactant. Hopefully that all erased? Yeah, that says reactant. Okay, if I want these pi electrons to react in their HOMO, what do I know about my reactant? I don't know anything about it. For these two species to react, what has to happen? For any two species to react, what has to happen? Maybe you mumbled something? What'd you say?
Molecular forces.
Right idea. What's happening with our intermolecular forces?
Control over electrons.
The flow of electrons. So if I want two species to react, what needs to happen?
There needs to be a place for the electrons to flow.
The electrons need to flow somewhere. These electrons, because we said I want the HOMO to react, I want these pi electrons to react. They need to flow somewhere. So I've got a source of energy, I've got a source of water. For them to react, they would have to flow to the reactant. Where do they flow to the reactant? To a LUMO. So here's a LUMO. Would I expect a reaction to occur?
No,
Why not?
because that LUMO is higher energy.
It's higher in energy than the other one. We don't expect that reaction to occur. For the reaction to happen, what must be true of our LUMO? Whoa, go away. What must be true of our LUMO and our reactant? It must be the same or lower. Arguably, it should be lower. If it's the same, what is the energetic favorability for the reaction to happen? Virtually none. Okay? So if I'm taking my two reactants, to get this reaction to occur, the LUMO of my reactant has to be lower in energy than the HOMO of this one. But what would that mean I need to do? What is the energy of each of those? And that's where it can become very challenging. Right? What if I wanted the pi system to react? I wanted to put electrons into the LUMO here. What do I know about my reactant?
It has to have a HOMO higher than the LUMO.
It has to have a HOMO higher than the LUMO of this one. Okay? So it's all about how those electrons flow to lower energy states. Okay? And that is challenging to numerically evaluate. So we tend to not worry about the numerics of it and instead could look at a reaction and say, this reaction happens. If it happens, what does that mean? The energetics have to be aligned properly for it to occur. Okay? So, if we get rid of all of that, there we go. We get our fun stuff. There's our 5 molecular orbitals. Our 10 electrons went into there. There's our molecular orbital, our LUMO molecular orbital for our pi system. Okay? Because those of you in lab reviewed that lab video. Am I recording? Yes, I am. Recorded our lab video, and we did ultraviolet spectroscopy. What is ultraviolet spectroscopy talking about?
Vibrating the bonds.
Vibrating the bonds is an awesome answer to a different question. That would be if I asked, what is IR spectroscopy talking about? It's the exchange of electrons. Electrons jumping where? From the HOMO to the LUMO. That happens to match exceptionally well for pi systems. This is why when you look at ultraviolet spectroscopy, most of the molecules you're talking about have massive pi systems. Okay, lots of double bonds. You might be like, well, I don't really believe that. How many of you have looked at the structure for any SPF sunblock system? Anybody? 2 people. So it's not a really good example. Feel free to look it up. Okay? And when you look up the structure for sunblock, guess what you find in it?
A lot.
A crap ton of pi bonds. Because what are the pi bonds doing? Absorbing ultraviolet light so that your skin does not. Okay? That's the whole point of sunblock. Absorbing ultraviolet light. Organic molecules do a phenomenal job of it, which is why we smear sunblock on us, because our skin would absorb it otherwise. Okay? So we could use that to our advantage if we were to study ultraviolet spectroscopy, which we will in the next unit, sort of. So let's just ignore that and just be excited that we've got an application of molecular orbital theory that literally just dawned on me as we were talking about it. Okay? So, summary. Sigma bonds. Sigma bonds are a direct overlap of orbitals. Okay? You'll notice we've got an extra little piece here for single bonds. Rotation becomes irrelevant. What happens? So here's my 2 orbitals with a direct overlap. What happens to the overlap if I rotate the bond?
Nothing.
Nothing happens. Which means what can single bonds or sigma bonds do?
Rotate.
Freely rotate. Okay? For those of you, if we really wanted to try this example, we could try it. There we go. What do you see right now? 2 markers, yes. What do the markers say on them? Expo. So if you drew that out, you could draw out your marker and you say Expo, Expo, right? What happens if we rotated it? Does it look like Expo, Expo anymore? No. So if you were to draw it out, would you draw the exact same thing? No. Would your 2 drawings look the same? No. Do they represent the identical structure? Yes. Guess what you're responsible for? Recognizing that that is true. Right? So an organic molecule is vastly more complicated than just 2 pens connected to each other. Any sigma bond can freely rotate, which means it could change the orientation of all the atoms relative to each other and make it look different. That does not make it a different molecule. Right? This is where the models can come in handy because you can get used to seeing how those things flop and bend around and not get lost in those. When we move to the pi bond was an indirect overlap of orbitals. So if we take the 2 same markers, they have to be in the same plane, right? So that we look at them from the side, what do?
They overlap.
They overlap, right? Kind of, sort of? Yeah. Sorry, the pen was open. What happens if we tried to rotate? The overlap disappears, which means
No longer a bond.
the bond disappears. What does that mean for us for pi bonds? Pi bonds don't rotate. We'd be going through a higher energy state because we've broken that bond. Okay? So pi bonds don't freely rotate. We would have to force them to rotate. Okay? Just because this also kind of tripped in my brain, and my brain's messed up sometimes, so why not? Here's our pi bond. Lowest energy electrons. If I want this to rotate, what has to happen to the pi bonding interaction? It has to cease. I have to make sure that the net interaction in that pi system is not bonding or anti-bonding. Right now I have 2 electrons in a bonding orbital and none in an anti-bonding, which would mean it's all bonding. How could I possibly counteract that bonding system? What would I need to do to one of those electrons? It needs to get pushed upwards. It would need to jump up here. Now what happens? The net is 1 bonding, 1 anti-bonding. We might say, well, the result is nothing. That's not really bonding or anti-bonding, except
Result is non-bonding.
our anti-bonding are always higher in energy than our bonding are lower in energy than our atomic orbitals. I know this looks nice and symmetric. It's not. So in this case, the average result here is
Pi bond, or I mean sorry.
anti-bonding. If it is anti-bonding, does it want to be a bond anymore? No. So do we have a pi bond? What can happen?
It gets shoved into a p orbital. Or
It can rotate. What have we just discovered? How humans see light. It's all about a single rotation. That single rotation can only happen because an electron has jumped from a highest occupied molecular orbital to a lowest unoccupied. That rotation is enough to set off neural pathways that we now interpret as light coming from a particular pixel within our own eyes. Molecular orbitals. They are insanely fascinating and cool. They're also insanely difficult to interpret. Okay? Bottom line, multi-bonds, don't rotate them. Okay? The only way we can get them to rotate is if we do something special. Okay? We're not doing anything special yet. Sounds kind of mean. Hybridization, the more we hybridize, the more orbitals are involved, the higher in energy. Why would it become higher in energy if we increased hybridization? What orbitals are we talking about? S. I meant to draw an S, not a circle. S and P. Anybody notice anything interesting about how I drew those?
put all three p orbitals higher than the S.
All three P are higher than the S, but all three P are at the same level. Why would I do that?
Because they're all equally.
P orbitals are all of equal energy, and our P orbitals are higher in energy than our S. So there's our diagram. As we increase hybridization, we have more orbitals. So we're talking about going from S to SP, to SP2, to SP3. Why would we be getting higher in energy? We have more P character. So if I looked at just the S orbital, I would say it's probably right about there. If I looked at the SP, where would its energy be? A little bit higher. Why would it be higher? It's the average of those two orbitals. The next one, a little higher still, a little higher still. So we're increasing energy. By increasing energy, our electrons are progressively moving further from the nucleus, which means it's effectively less electronegative. So we can use hybridization to predict reactivity. You don't want to do that, that's fine, you memorize. Okay? So those are our big lessons out of our molecular orbital theory. I do think it's kind of neat. Okay? But we don't really use it often enough, at least in my version of the class, to really dig too much more into. Okay? This also changes when we look at those averages where our electron densities are located, which is also going to dictate how our individual reactions work, which we might do when we move into reactions with a bond between carbon and chlorine. I don't want to draw it out now because that's minuscule aspect of relevance to how I teach the course. Okay? So we won't address that, but we could look at it later. Which gets us to my least favorite subject, nomenclature. Okay? This slide, and I'll try and work on it for future slides, but this slide is slide number 64. Okay? And the reason I mention that is that you should memorize everything on this slide. Okay? This isn't like you can apply things. Nomenclature is literally what is the name. You have to know the rule. If you don't know the rule, you don't know the name, you're dead in the water. Okay? What is on this slide, I would argue, is if you look just at nomenclature as a subject, what is on this slide is probably a D letter grade, right? For just nomenclature. Okay? It makes up less than 10% of your exams, which means even if you got 50%, you're still getting 5% of the nomenclature. That's, to me, a pretty decent return on investment, okay, when it comes to nomenclature. If you got one of those steel trap minds where you can lock down all the nomenclature rules, have at it, have fun with it. The textbook's there. There's a textbook called the Gold Book for nomenclature knock yourself out. Okay? But this is the bare minimum. Okay? Some of which won't get discussed this semester. This is literally everything. Okay? Most of this semester is going to sit looking at alcohols, alkenes, alkynes, alkanes, ethers, and our halogens. We will not look at amines, ketones, aldehydes, esters, or acids. Those are all reserved for second semester nomenclature, though you will see them pop up in your readings, okay, for how to name them. Basic structure through that middle is we have to find our highest priority functional group, and the naming of the end of the name is based on that group. So if my highest priority functional group is an alkane, the end of the name becomes ane. There it is. What if there's an alkane and a ketone? Well, then the ane ending has to change. What does it change to? Well, I'm going to subtract the E, still keep the ane, but now I have another piece to add in. That extra piece is one, representing the ketone. Kinda, sorta?
Yep.
What if you had two high priority groups, like an alcohol and a ketone? Alcohols would change the ending, and it would be an-all. But if I had a ketone also, I can't have the all and the one, because they're both ending names. The alcohol, because it's lower in priority, gets a prefix as a substituent and gets called hydroxy. Okay? So the name before the arrow is, this is the name of that functional group. The name afterwards is, we have to modify it because it's not the primary functional group. Right? That's the basic of those patterns. Right? Highest priority to lowest priority, depending on what textbook you go into, you'll find there's tons of other functional groups that also can insert themselves into this. Okay? Those would be kind of that part of the 40% that I'm like, I don't want to worry about. Okay? Number of carbons. Right? I've got up to 6 highlighted. I would argue you should probably go all the way up to 10. If you want to pass the class, you need 6. Okay? You want to do better than pass, you need 10. Okay, after that, we don't need to worry about it. These would be the prefixes counting the number of carbons. Functional groups are listed as extra little pieces. We know they're functional groups. Shoot, I thought it was on there. Because it'll show an ending of YL. Okay, so if I had a 1-carbon functional group, a substituent, I would know that as meth, because it's 1 carbon. And I don't want to end it with ane because that's the ending of the structure. It's a substituent. I change the ending to YL, and I get methyl. Okay? Rings and cyclic structures are just a giant freaking mess. Okay? So, as several people have found out by already looking at the nomenclature in SmartWork, rings are a mess to deal with. You get rules and subrules and subrules of subrules. Right? You just kind of have to deal with it and get them exposed. Right? And then your basic assembly down below. Find your longest carbon chain that contains the highest priority. Identify your functional groups and substituents. Define locations. Okay? The locations, there's all sorts of nasty rules on this. You want to use your smallest number for your highest priority functional group. If there's a tie, then use the smallest overall numbers. Okay? If there's still a tie, goes alphabetic. If there's still a tie, it goes to the most points scored. It's literally that dumb. Okay? The most points scored was a reference to like World Cup breaking of ties. If you didn't get it, don't worry about it. Okay? Not relevant to nomenclature. Then you'd put your name together, alphabetical order. Substituents listing. Not numerics, alphabetical order. Bromo comes before chloro. Okay? Trimethyl versus propyl. Which one comes first? Trimethyl or propyl? Trimethyl, but doesn't T come after P? Yeah, but M comes before P. Okay? So the prefix numerics doesn't affect the order. Yeah, don't look at me. Okay? So, identifying main chains. You're responsible for formulas. You're responsible for structures. Okay? We've got a perfect example running directly across the top. That first one has how many carbons in it? 4, which means bute. Okay? What is the hybridization of every single one of those carbons?
SP3.
SP3. So I like to think of this as a hybridization addition. That hybridization means I need the AN. So it's butan. Are there any other functional groups? No, which means the alkane is my highest priority functional group. Butane. The next structure to its right, does that look the same?
Yes.
Does it look the same? Come on now.
No.
Eyeballs. No. Is it the same?
Yes.
Yes, you're responsible for knowing that distinction. Okay? The next one to the right. Does that look the same?
No.
No. What happened?
One of the sigma bonds rotated.
We did a sigma bond rotation. Okay? This is one of the reasons why nomenclature is so powerful. If I go through to name the middle one, 1, 2, 3, 4 carbons, which means but, all sp3, ane, only sp3, butane, last one, 1, 2, 3, 4 carbons, and I get but, all sp3. Only thing there, ane. Does the name change? No. Nomenclature can call attention to just those single bond rotations. Okay? I would argue working with the models will also call attention to it and can call attention to it faster than naming a structure. Because will you get name butane? You're going to get name this beast. Yeah, the long pause was kind of telling. Okay? It takes time to go through and process those. What was step 1? Longest carbon chain.
9.
This is typically what people would go through and do, and they'd say 1, 2, 3, 4, 5, 6, 7 carbons. Yet somebody went through and said 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. But it wasn't in a straight line. Doesn't matter because sigma bonds can rotate. It's drawn in such a way that it is not obvious the longest chain. It will always be drawn like that. So if you go through to solve a nomenclature question by just going straight across, you're probably doing it wrong. Look off axis. Yes?
Shouldn't you flip those? The numbers?
I didn't actually number any of those yet.
Oh, okay.
Okay, my first recommendation, some people have fancy tools and could highlight. That's a good idea. This works for me for circling. All right, that had 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons means
No.
non. What's the hybridization? Ane. Do I have any special functional groups? Beyond sp3 carbons? No. Non-ane. The next part. That's not named in the non-ane. It's hanging out of my highlightation. So I need to name that. Not yet. Jiminy. Calm down. I got 3 pieces hanging outside of that main chain. I want to go through and name them. Green one. How many carbons?
3.
1 carbon, which means meth. Because it is a substituent, I get methyl. Blue one. 2 carbons, so I get F. Because it is a substituent, ethyl. Black one. 2 carbons, so ethyl. Now I could try and put this name together. Ethyl comes before methyl. So I want my ethyls coming first. I don't know why I switched colors there. What was it, green? How many ethyls were there? 2. So I can drop it in as a diethyl. Now I have to reference where every single one of those stupid functional groups are. Before I even deal with counting, because I know my instructor hates nomenclature and doesn't want to deal with this, I'm going to immediately check the multiple choice answers and say, does that get me an answer? If it does, I don't care about where the numbering is. I'm done. I'm moving on. Okay? If not, I'm going to have to deal with the numbering. There's two ways I could number this, left to right or right to left. Which one should I try first?
Right to left.
Right to left. Why? Because everybody reads left to right, which means if we're going to build a question with nomenclature, we're going to put two answers in there. One numbering left to right, one numbering right to left. People that aren't paying attention will number it left to right because they read English. And we read left to right, top to bottom. So when it comes to nomenclature, do everything the opposite of how you would normally do it, and you're probably going to get to the correct answer. No guarantees, okay, but probably going to get there. So why is numbering 1, 2, 3, 4, 5, 6, 7, 8, 9? That's a 9. Jiminy, man, monkeys, and dogs, as opposed to 1, 2, 3. Why is purple better than red? Methyl shows up at position 3. Ethyl, the first substituent, would show up at position 4. First substituent at 3, that's my better sequence. That means 3 methyl. And where are my ethyls? 4 and 6. I have to specify both of them. I will specify it with a comma in between. What if both methyl or both ethyls were at the exact same position? I still have to name both of them. A single number corresponds to a single substituent. If you have multiple substituents, you need multiple numbers. Okay? Extra little nasty nuance behind this, which you never get tested on, so it's not a big deal. Commas in between your numbers. Anywhere you have a number to a letter, you need a dash. Okay? So for putting all of that together to get the name, you'll also notice there's this giant gaping space here. Why is there that giant gaping space? Because it's an artifact of how I assembled the name. Should it be there? No. What if you include it? It's wrong. Okay? If you go through and look at the smart work, you will notice I do not have any type in the name questions. Why? Because of those mother effing spaces, dashes, commas. There's a multitude of places that naming goes sideways very fast and for inherently stupid things. Make sense? Okay. So, what's in a name? Draw these structures. These are arguably the easier way to go, structure, or from name to structure. Done at 45, you get 2 minutes. Okay, I think I've got them. If we start with the first one, we've got kind of written underneath each of the different colors what I would break it down to. And if you look at it at home, you'll be able to see the colors better, but each of my drawings include that color coding behind it. So that first one, we've got 6 carbons. They're all sp3. At position 3, I have my methyl, so I'm showing a CH3. It does say di, so I need a second one. Do I have to specify CH3?
No.
No, because every point by definition is a carbon. Okay? With only one bond shown, that's an implied 3 hydrogens, and I get a methyl there. Yes?
Does it have to be drawn like yours, or can it be like
Oh, I know what you're talking about.
Does it have to be that specific to that?
I believe what you're saying is, could you draw it this way?
Yeah.
Okay, we'll address that in just a second. First, before we deal with your question, what's wrong with the name?
Have 2 numbers for the 2 diamonds.
Right. This name is problematic because I haven't specified the location for both methyls. It only says 3. By definition or by interpretation, you probably placed it at the 3 position. You're like, well, couldn't we just get away with that? You're making an assumption about the name. That makes the name invalid. So you're not allowed to do that. Okay? So you have to specify that. As to drawing the methyl straight down, as what I've just switched it to now, for the sake of naming and drawing structures and figuring out answers, probably not. Okay? for the sake of doing reactions and drawing proper structures for potentially online homework systems, yes, it is inherently a bad thing to draw it that way. Okay? And the reason being, what is the hybridization of that carbon? sp3, which means it's what geometry? Tetrahedral. There is no way you'd be able to draw that. Okay? If you added wedges and dashes to it, then maybe you had an argument. Right? But when we try and draw out our structures, if you want to think about your tetrahedral carbons as a connection of four things, okay, and here it's not a horrible idea or horribly drawn, but you could get away with it. Two solid lines making a V, right? Everybody see the V? And now we're going to make an upside down V. Okay? For it to be a proper tetrahedral structure, one V needs to be wedged and dashed, the other one needs to be solid. If you drew it this way, that is physically impossible. There is no way you would be able to organize a model to allow that structure to be valid. Okay? Because of that, SmartWork will complain at you. You may not like it, I agree with it. SmartWork should be complaining at you for that. It's such a subtle difference, but it can make a huge difference in interpretation when dealing with Chapter 5 and reactivities. Okay? So remember that when dealing with your structures. Upper right-hand corner, we've got hex for the 6, sp3, all single bonds. Cyclo means ring, so there's my ring. And then it says 3-dimethyl. So one suggestion was the problem with this name is it didn't specify both. And I'm going to argue that that is not valid. What is wrong with this name? Shouldn't even say 3. 3 is wrong. Where's position 3 on this structure?
Anywhere?
No, it's either here or here. Your substituents on rings are by definition at position 1. So to fix this name, we could have erased the 3 and just gone dimethyl cyclohexane. That would be acceptable. More appropriately would be 1,1-dimethyl. Okay. IUPAC is a little bit wishy-washy on that, including the 1,1s. They're trying to push for more accuracy and saying it's required to say 1,1. There's enough people that think it's nonsense that that's not getting pushed too hard. Okay. We move to the bottom one, 3-dimethyl hexane 2-ol. We've got our 6 carbons, so I drew out the 6 carbons again. Okay, all sp3 hybridized. Position 2, I have an ol. The ol is the ending for an alcohol, which means I know I have an OH at position 2. So 1, 2, I've got the OH. The dimethyl, there's my methyls. Again, that should be 3,3-dimethyl. Kind of makes sense? Yeah?
Why do you count it backwards, like or left to right?
Why did I count left to right as opposed to right to left?
Yeah.
Which way do I read?
Left to right.
Well, I read left to right, and so that's how I naturally and instinctively drew it. In the case of an exam, what you're likely seeing is nomenclature showing up in multiple choice. Would be drawing out the structure this way a good option? Probably not, because the multiple choice answer is probably going to have it numbered right to left. Okay? So if you were trying to draw the structure for the name, you probably want to always count right to left, because it's probably more likely to match your answer choices. It's all on probabilities there. You might be 70% of the time. 30% of the time, it'll run exactly like this. Right? On top of which, what else could happen in this? Could have drawn it that way. And now everybody goes, oh, that can't possibly be right. It's the same number of carbons, right? 1, 2, 3. Yeah, same number of carbons. All we did was fold it up on itself, and that all of a sudden makes it impossible to see the answer. Okay, so be aware of that. So yeah, numbering left to right and right to left is ultimately arbitrary. It's just a question of getting in the mind of the test taker or the test maker.
So you can do this right however you want, and then like
You can draw it however you want, but realize on a multiple choice answer, whatever you draw, you then have to prove is the correct answer by matching it to the answer choices. Okay? And that's one of the problems with OChem, is there's so many different, I would not say drawing is dangerous. I would actually argue that drawing is better than trying to do it in your head, because you're going to end up shuffling all four answer choices. And 3 out of those 4 answers are wrong. So you could very easily confuse yourself by looking at those.
Okay.
A lot of that is your personal taste. If you're good with doing that, by all means go ahead and do it. My experience, you're better to draw it out. Okay. Questions on our nomenclature? Kind of get it? Okay. We move to alkenes or alkynes. Okay. I actually don't want to go through all of these, but we'll pick the upper right-hand corner one. When we go through and look at this functional group, we have to identify the longest carbon chain. Very often students will go, 1, 2, 3, 4, 5, right? 5 carbons. Everybody see that? It's a nice long carbon chain. Remember, when we find our long carbon chain, though, what must it include? The highest priority functional groups. What's your highest priority functional group in that structure? The alkene is important. I would argue my numbering system did include that, though. The alcohol is the highest priority functional group in this case, which means your numbering must include the alcohol in that backbone. Where we'd had it numbered before did not include it, which means that is invalid. So we could go through and say, well, how about this as our longest chain? Because that's 4 carbons as opposed to, wait, they're both 4, aren't they? Never mind. 4 or 4, which way, blue or red?
Blue.
Blue because?
The 4 O's.
You need the alkene. Okay. So we've got the alcohol, 1, 2, 3, 4 carbons. So we've got a bute. What's the hybridization? Highest order hybridization? With that pi bond in there, we're looking at sp2. sp2 is an ene. We have to specify where each of those substituents is located. The alcohol is the highest priority, which means it is connected to position 1-1. Where's the ene? Position 2. So just the main chain is but 2 ene 1 all. Yes, that's how you have to name it. It sucks. Okay? We also have some substituents floating around out there. What do we switch to? Orange works. We have some chloros. How many chloros?
2.
So we have a dichloro. Where are those chlorines located?
3, 4.
3 and 4. Remember, our numbering happened from the alcohol. 1, 2, 3, 4. Okay, and now the fun and exciting one. How do you name that?
Methyl, methyl.
Okay, there's 2 names that can come out of that. One that's the most straightforward would be isopropyl. Okay, and for the uninitiated, if we look at this shape right there, everybody see that kind of shape? Doesn't that look kind of like an iso? For those of you wondering what I'm asking, I asked the same question, but that's an iso. When you see the word iso, that shape is there. Okay? So iso, that shape, how many X carbons part of it? Well, that shape inherently includes 3 carbons. So the smallest iso you can get is isopropyl. Okay? But we can get isobutyl by doing what? Including an extra carbon. Now it's isobutyl. Okay? So we could call it isopropyl, and again, for those of you who are being like, well, that's a dumb name, how would I ever know that? You're officially not responsible for that, though it is, we run in some borderline cases there. Okay? We have to break the substituent down into pieces because it is a chain with a substituent, and the substituent has a substituent. There's 2 carbons within that, which makes it an ethyl. There's a methyl attached to said ethyl. The methyl is attached to which carbon of the ethyl? Should it be numbered 1, 2, left to right, or 1, 2, right to left?
1, 2, because you have to have your substituent on the, oh, sorry, 2, 1.
Left to right, your numbering on your substituents will always start where it attaches to the main chain. So that is a 1-methyl ethyl.
Wouldn't it have to be by default?
What's that?
Would it have to be by default?
Because
Depends what you decide is default.
I mean, like, if you had a 2-methyl ethyl, that's really just.
Propyl. You could build, in this case, yes, you could build other structures where that isn't a default.
Oh,
Okay? So how do we put this huge freaking beastly name together?
1-methyl ethyl 3,4-dichloro-2-1-all.
So I'm going to make an argument that what was just suggested is wrong. We do not start with the 1-methyl ethyl. We'd start with the chloro because C comes before E. Okay, and I really don't want to write all that out. Okay, so we're just going to say, whoa, 3,4-dichloro. There's our dash, dash. And now we'd move down to the next part of the name. Where is the methyl ethyl located? On the second carbon. So we have a 2, 2 comma 1.
2 parentheses 1.
Parentheses 1. We've got a shift there. We need that hyphen 2, parentheses 1, methyl, ethyl, but 2-ene-1-all. And if we thought that was it, it turns out it's not, but we aren't going to worry about that nomenclature system because that requires the 3rd chapter of nomenclature, and we aren't there yet. Okay? Because there's another layer of crap that we have to layer onto that. Okay? So all together now, 3,4-dichloro, 2,1-methyl ethyl but 2-ene-1-all. Anybody understand why I might not like nomenclature? Okay? That said, it is important, and I do want you to practice it. Okay? My personal experience, that is up to you to decide that for yourselves, and you can agree with me, you cannot. It's entirely up to you. I will say probably one of my personal things that I need to work on and fix is that when we look at the ACS and I classify questions out as to what topic they're on, nomenclature is the lowest performing for students. Okay? In my experience, or my perceived experience, it's usually the highest performing. So for all of my students to be low performers in nomenclature, you're taking after me. As long as you take after me and do really well in every other part, I'm okay with that. Okay? If you need to balance it out with some nomenclature. Okay? The last one down here, if for whatever reason you get excited and want to jump into nomenclature chapter 3, this is a hard structure to name fully outwise because those 2 double bonds are different. One is cis and one is trans. So you'd have to make sure you numerically arrange them appropriately in the name. Otherwise, you're wrong. There's like rule, subrule, subrule, subrule. There's the rule on how you get down to there. And it's not obvious. At least it wasn't to me. Okay? I'm done with nomenclature. I want to get something into something more interesting. Okay, in the last couple minutes. So now what we jump into would be Chapter 4, our butanes. Okay? Chapter 4 is now looking at different ways to represent our 3-dimensional structures. We've already started to hint at this. Okay? If we were to draw out the Lewis structure for a butane, what might we draw? 4 carbons in a straight line. Okay? We could have also drawn it that way. Formulas suck. Look at your structures. Okay? Those structures have the same formula, but they're different somehow. Okay? So we would need to define that relationship. How could we define that relationship?
Is that even?
How many carbons are there?
4.
How many hydrogens?
No.
It is sp3. Those two formulas have the or compound structures have the same formula, same hybridizations. They're both butanes. Okay? In this case, the butane is just saying there's 4 carbons.
Oh.
We aren't saying it is butane, the name, 4 carbons in a line.
Gotcha. Okay, that's what I was confused.
Okay? What is that relationship? Should we call them different?
Yes.
How many carbons? 3 carbons. So you're telling me the relationship between the 2 nicely drawn black structures and the relationship between the black and the red structures should be called the same thing.
No,
Why not?
because they have different, they're built differently.
They have different
They are built differently.
differences. Okay? So I can't use the word different to represent both differences because they're different for different reasons. Okay? Feel free to sprinkle in some more differences.
They have different bond arrangements.
We need to go through and be extra careful with our phrasing. This last structure is different than those 2.
It's not a butane.
These 2 have the same formula, but a different arrangement of the atoms. Yes, I know I just said the word different again. Okay? I have to use another word to describe the differences between those. Okay? That's chapter 4 and chapter 5 ultimately. It's just saying what is the relationship between all of our structures and how can we visualize that relationship. Both 4 and 5 are huge for model kits because we're looking at that 3-dimensional model and saying how do we visualize these things. If you can't visualize the 3-dimensional orientation of these structures, you need a model kit or you are accepting probably 30% of the points gone outright wrong. Barely passing. That is how important this relationship is. Okay? With that, we're done. We'll be doing chapter 4 on Wednesday. For the record, chapter 5, I'm just saying we're not getting to. Okay? There's too much.